Hey guys, this is Mr. Barthel, and this video is to kind of go over the semester review and to give the answers for that. Basically, it's a pretty long review. It's probably broken down about 4 videos or so, and so I'll try to explain it in some detail, but not enough that it takes an hour to watch all the videos. So, number 1, going back all the way to the first week of school. Talking about forces and sort of free body diagrams. So list the forces that act upon versus a person standing on the ground. So I'm going to do it on a separate sheet of paper here, so that way I have plenty of room to show work and do what I need to do. And I recommend you do that as well. So 1A, what do we have? A person standing on the ground. So a person is standing on the ground. What do we got? First off, we know that on Earth, gravity is a force that acts on all students, or all things. So first off, we have the force of gravity. And we have to ask ourselves, is forces pulling us downward? Are we moving down? No. Or if we're standing on the ground, no, we're not. We're not moving down at all. That means there has to be a force to balance the downward force, or else we would go down. But we're staying stationary, so there's an equal force going up, and this is called a normal force. F normal, or just Fn if you'd like. So the two forces for that are normal force and gravity. For number 2, a ball that's thrown into the air. If the ball is already in the air, if it's just in the air, then gravity acts on it, and gravity alone acts on it. But if we're actually talking about the throwing, the motion, where the person is throwing the ball, then you have the force of the throw. So the force of the throw, and the force of gravity, Fg. So in the case where it is being thrown, obviously the force of the throw has to be bigger than the force of gravity, so that way it actually moves. So if we draw the ball, we have the force of gravity. If the ball is going to travel upward, then the net force has to be in the upward direction. So the force of the throw would look something similar to that. Alrighty, for 1C, we have a car driving at a constant speed. This is very important. So you got a car, draw a little car, and draw a little free body diagram here. First off, what acts on all things on Earth? Gravity. The car is not going through the road, so there's got to be the normal force of the road. And then the car is driving at a constant speed, so something's got to be propelling the car. And we can say that that is the force of the motor. So it's pushing it this way. And the last part, or the fact that it's going at a constant speed, is one of the important parts of this. So a constant speed means that there is no acceleration. There is no change in motion. It has motion. It's moving across the road, but that motion isn't changing. It's going at the same speed. So constant speed, no acceleration, no change in motion. That means that the forces are balanced. This is Newton's second law. There is no acceleration, there is no net force. So the forces are balanced. So there is an equal force that opposes the force of the motor, which is I guess you could say air resistance, force of the air. There's also some frictional force and that sort of thing. But the important thing is that the forces are balanced. Space shuttle orbiting the Earth, that's easy. Got gravity. I'm just going to write gravity on that one. There's no air resistance up there. Assuming that the rocket isn't propelling the space shuttle, which typically they don't in orbit, then we only have gravity acting on it. Alrighty? So, for number 2, soccer ball kicked with a force of 20 newtons to the right at 90 degrees and 10 newtons straight forward at 0 degrees. What direction will the ball travel after being kicked? So if we remember, this is vector addition. So we need to make a scale. We're going to say that 1 centimeter is equal to, let's go with 5 newtons. Remember, 20 newtons of, our two forces are 20 newtons and 10 newtons. 20 newtons and 10 newtons. And so that means we can set a scale of 5. We pick a point. We have 20 newtons to the right, so that is 4 centimeters to the right. I'm not having a protractor because it's just right angles, so I'm going to try to be as precise as possible. So 1, 2, 3, 4 centimeters. And straight up at 0 degrees, we have 20. Oh, excuse me, we have 10. So that would be 2 centimeters. I believe I might have made a mistake right here. What do we have? To the right is actually 0 degrees. That's what I meant. And straight forward would be at 9. If we take our typical mathematical axis, then to the right is actually 0 degrees and upwards is 90 degrees. So my mistake there. Basically, the important thing is the process of adding the vectors. And so our net vector, this was force 1, this is force 2, so our net force goes from the dot to the tip of the final vector. This is our net force. Remember, you can use our scale to find the strength of that force. So it is 4.5. So 4.5 centimeters long. Our scale is 5 newtons per centimeter. So that comes out to 22.5 newtons. And the angle we will find is, my protractor, excuse me, approximately 28 degrees or so. So you may want to refresh that. Number 3, what does inertia depend on? Inertia. Inertia is a property of matter that basically says how hard it is to move it, how hard it is to change its motion. A car has a lot of inertia. This little pen here does not have a lot of inertia. You can move this pen really, really easily. If you go to a car and just try to push it a little bit, obviously the car is not going to move because it has a hole. You have to push a car very hard. So inertia depends on how much mass something has. So inertia is equal to mass. I'll just put that. Something has a lot of mass, has a lot of inertia. It's hard to move. So if the question asks which has the smallest inertia, mosquito, car, or cruise ship, a mosquito has the smallest inertia because that is the one least amount of mass. Number 4, a space probe is carried out by a rocket into outer space, and after the rocket uses all of its fuel, it continues to move on its own in a straight line. Why? Newton's first law, the law of inertia, says that an object in motion stays in motion unless acted upon by a force. So the rocket is already moving, and whenever the rocket run out, unless there's something to slow it down, it's going to keep on moving. And in space, there's nothing to slow it down. So that rocket will keep on going indefinitely until it hits a planet, hits an asteroid, or it can find more fuel to blow the opposite direction or whatnot. So it stays in motion until acted upon by a force. Number 5, Newton's second law. What is Newton's second law? Newton's second law is generally remembered by the formula F equals ma. It shows that the amount of acceleration that something has is proportional to how much force you give it. So if you give it lots of force, or if you give it more of a force, then the acceleration is going to be more. Likewise, it's inversely proportional to mass. And so if there is a lot of mass with the same amount of force, it's not going to accelerate as much. And that goes back to the car. If you apply a force to a small mass, it can have a big acceleration. So if the mass is small, it can have a big acceleration. Whereas if the mass is really, really big, like a car, then it's going to have a really small acceleration with an equal force. So F equals ma typically summarizes that. And acceleration, again, is a change in motion. That's number 6. It's different from velocity. Velocity is just a speed. If you're going 60 miles an hour, 30 meters per second, those are speeds. And acceleration is a change in speed. So you're speeding up or you're slowing down. You're going from trying to pass the guy on the highway, so you speed up to go from going 60 to 65 or 70 to pass him up or whatnot. So that is an acceleration. Where am I at? I'm at 11 minutes here. Do one more. Number 7 is what is a net force and what happens if the net force is 0. So number 7, a net force is the sum of all the forces. So like in number 2 up here, we had 2 forces acting on the soccer ball, and the net force was the combination of those 2 forces. So you had one force to the right, one force up, so the combination was kind of up here and to the right. All right. In this car, the net force was 0. So we had force up, down, left, and right, but they all canceled each other out. So the net force was 0. So what happens if the net force is 0? Forces are balanced, constant speed, or if it's not moving, it's not going to move at all. So how we typically phrase that, there's 2 ways. So if the net force is 0, then the motion, whatever its motion is right now, does not change. Motion does not change. What does that mean? If it is already moving, it's going to keep on moving. Like the car is driving down the highway. The net force is 0. It doesn't mean it's not moving. All right, that kind of answers the last part of that question. It says, is it possible for an object to be moving and the net force be 0? Yes, it is. The car is, if you're going at a constant speed, that means that your motor is giving just enough force to balance the wind force slowing you down, the wind resistance. And also the road is balancing gravity. So all these forces are balanced so that you can maintain a constant speed. Your motion does not change. Whereas if you slow down, you have to let off the gas. So you have to basically decrease the force that your motor gives to slow down, or you increase the force to speed up. The way you think about it is an elevator. If you are in an elevator, whenever you first get in and you push the button and you feel that sensation in your stomach, well, what you're feeling is you're being accelerated upwards or downwards, whichever way you're going. And so you feel that force in you, but you don't feel it for very long. Afterwards, the sensation goes away. And because the motor adjusts its pull so that it's not speeding you up anymore. Now you're just moving at a constant velocity. You're going up, 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 up. If you listen to the rings of the elevator, you notice that you pass by each floor. It takes about the same amount of time to do it because you're going at a constant speed until it slows you down. And once it slows you down, now you have your motion has changed, and so you feel that feeling again in your stomach, like, ooh, what's there? So those numbers 1 through 7, and that was basically what we talked about for the first 4 or 5 weeks of school or so. Next video we'll go over the next questions, which is mostly impulse and momentum and into energy. So stay tuned.